Dah. Hello everyone. So today we will present question 2, group B. So the first question, sketch the graph of FT. So FT is a piecewise constant graph. So from time between 0 to 1, um, FT is 0. So here we have um, um, a filled circle and this is an empty circle, which means it's not hitting one lah. It's between 0 to 1, but it's not 1. And then from 1 to 3, the piecewise constant is 4. So we have here, and then um from t above 3, the piecewise constant is -2. So this is the graph of FT. And then for question B, express FT in terms of unit step function. So at t equals to 1, FT changes from 0 to 4 units. It rises from 0 to 4. So we add 4 unit at t equal to 1 to represent this change. At t equals to 3, FT drops 6 units. So we subtract 6 units at t equal to 3 to represent the drop. So the complete unit step function is 4u at t equal to 1 minus with 6u at t equal to 3. For question C, we have to apply the Laplace transform method to determine the frequency domain xs. So first, we substitute the constant values given in the question where m is equal to 1 and k is equal to 16 into the differential equation, and we get this equation, and then we apply the Laplace transform on both sides. So for when we apply Laplace transform to x to the power of dx to the power of 2, we get x square xs minus with s at x equal to 0 minus with x prime 0. And then we substitute the initial value where x at time 0 equal to 0 and x prime at time 0 equal to 0. So we get only x square x at the frequency domain. And then the second one, the 16 Lx equals to 16x s as a frequency time domain. We use the Laplace transform. That's like a table. So we see the conversion table and we transform the differential equation into the frequency domain. And then finally, for the right-hand side, we have to transform the FT, the unit step function. So there's two parts. One is the 4u at t equal to 1 and 6u at t equals to 3. So when we transform a unit step function, we get e negative to the power of negative cs over s. So c is the time, t equal to what time. So we get 4e minus 1s. So we get minus s over s minus with 6e to the power of negative 3s over s. And then we substitute into the equation and we factor out the xs, the frequency domain. So we solve for xs. Now for question D, we have to determine we have to convert from the Laplace, the frequency domain into the time domain. So we have to inverse Laplace transform. So likewise, there are two terms here that we have to inverse. So first we factor out the delay. The delay is the e to the exponent 1. That is the delay. So we factor out the delay. And then we Laplace transform the non-delay first. So the inverse Laplace transform of the non-delay is for 1 over s bracket x square plus um, angular frequency square is equal to 1 over angular frequency square 1 minus cos angular t. So we just apply, like we factor out the 4 first, and then we apply the inverse Laplace transform, and then we multiply by 4 back. So we get 1 over 4, 1 minus cos 4t. And then we inverse the delay, we get the unit step function that we got above. We inverse back. So we multiply both of these, we get u at t equal, wait, u at t equals to 1 multiplied by 1 over 4, 1 minus cos for t equals to 1. This is the unit step function at t equals to 1. And the second term, we do the same. We use the same because they are in the same form. So we get the 1 minus cos 4t again. And the radian is 4 square. So just substitute, and then we get this. And then we do the same like we did before. And we combine both terms. So for x at the time domain, we get u t u at t equals to 1 multiply with 1 over 4, 1 minus cos for t equals to 1. And then u at t equals to 3 minus multiply with 3 over 8, 1 minus cos for t equals to 3. Okay, so for question E, we have to use the undetermined coefficient. I choose to do the undetermined coefficient method because it's simpler. For at ft equals to 4. So substitute into the ordinary differential equation and we solve. This is a non-homogeneous equation. So we have to get the solution for the homogeneous and the non-homogeneous part. So for the homogeneous part, we find the characteristic equation r squared plus 16. So the root of the characteristic equation is 4i. So because what the root is below 0, so the solution will take this form, C1 cos the imaginary part plus C2 sine the imaginary part. So we get the complementary function, the solution for the homogeneous equation, C1 cos 40, which is 40 is the imaginary part, plus C2 sine 40. And now we solve for the non-homogeneous part. Since ft equals to 4 as a constant, we assume the solution is also a constant. So we assume that xp equals to a. And then we differentiate xp twice, we get 0, and then we substitute back into the equation, 16a equal to 4. So a is equal to 1 over 4. So the particular solution is 1 over 4 for xp. And now we combine the general solution. We combine both of them, we get this. And we apply the initial value problem where x at time equal to 0 equals to 0 and x prime time equal to 0 equal to 0. We substitute back into the general solution. So C1 we get negative 1 over 4. Now we have to differentiate x to use the second initial value. We get C2 equals to 0, and then we substitute, we get negative 1 over 4 cos 40 plus 1 over 4, or we can simplify in this form. So how we check our answers correct? So this and this from part D, we substitute T equals to 4, and we will get the same form. If we substitute the time domain at T equals to 4. Okay, so for question F, which method do I prefer? I prefer Laplace transform method because it simplifies the initial conditions, piecewise functions, and exponential terms into algebra all at one time. So I do not need to repeat my calculation 3 times for different values of ft like I did with at question E. F equal to t, f equal to 0, f equal to -2. I don't have to repeat 3 times. The Laplace transform method turns differential equation into algebraic equations, which simplify the solution process. So that is all from us from group B question 2. Thank you.